Ever wondered how AI can create stunningly realistic images of people who do not exist, or generate entirely new pieces of art, music, or even complex protein structures? The magic behind many of these incredible feats is a revolutionary class of neural networks called Generative Adversarial Networks, or GANs. At their heart, GANs are built on a fascinating concept: two neural networks competing against each other in a zero-sum game. Think of it like a highly sophisticated game of cat and mouse, or perhaps even better, an art forger constantly improving their craft while an art detective gets better at spotting fakes. In a GAN, these two competing networks are called the generator and the discriminator. Let us meet our first player, the generator. This is our talented art forger. Its job is to create new data from scratch that looks incredibly realistic. For image GANs, its input is typically just random noise, literally a string of numbers that mean nothing. From this noise, it tries to conjure up an image that looks like it belongs in the real world. Then we have the discriminator. This is our astute art detective. The discriminator's job is much simpler. It is a binary classifier. It receives two types of input: real data from our dataset and the fake data produced by the generator. Its task is to correctly identify whether a given piece of data is real or fake. The true genius of GANs lies in their training process. It is not sequential. It is an adversarial loop where both networks continuously improve by trying to outwit each other. Let us break down the training cycle into two alternating phases. Phase 1, training the discriminator. In this phase, we want our detective, the discriminator, to become really good at its job. We feed it a batch of real data, and we tell it this is real. Then we feed it a batch of fake data generated by the generator, and we tell it this is fake. The discriminator learns to adjust its internal parameters, its weights, to minimize its classification errors. It is essentially learning what makes real data real and fake data fake. Phase 2, training the generator. Now it is the forger's turn. With the discriminator's weights temporarily fixed, we train the generator. The generator produces its fake data, which is then fed to the discriminator. But here is the crucial part: the generator's goal is not to create good images directly. Its goal is to create images that fool the discriminator. If the discriminator classifies a fake image as real, the generator gets a positive signal. If it classifies it as fake, the generator gets a negative signal. The generator then adjusts its own parameters to generate fakes that are more likely to be classified as real by the now smarter discriminator. This cycle repeats thousands, even millions of times. The discriminator gets better at spotting fakes, forcing the generator to create increasingly sophisticated and realistic ones. Eventually, if the training is successful, the generator becomes so good that the discriminator can no longer distinguish between real and fake data. Its probability output for a generated image will be around 0.5, meaning it is guessing randomly. This entire setup is adversarial because the two networks have opposing objectives. The generator wants to maximize the probability of the discriminator making a mistake, classifying fake as real, while the discriminator wants to minimize that mistake. It is a mini-max game where one player's gain is the other player's loss. So, what can this powerful adversarial training achieve? The applications of GANs are vast and constantly expanding. 1. Realistic image generation, the most famous use case. Generating incredibly lifelike faces, landscapes, animals, or objects that have never existed. 2. Image-to-image translation, transforming images from one domain to another. Think turning sketches into photorealistic images, or day scenes into night scenes, or even horse photos into zebra photos. 3. Style transfer, applying the artistic style of one image to the content of another. 4. Super resolution, enhancing the resolution and detail of low-resolution images, making them sharper and clearer. 5. Data augmentation, creating synthetic, realistic training data to expand datasets. Especially useful in fields with limited real data like medical imaging. 6. Text-to-image synthesis, generating images purely from textual descriptions, leading to fascinating creative possibilities. 7. Drug discovery and material design. While still nascent, GANs are being explored to generate novel molecular structures with desired properties. Despite their incredible capabilities, GANs are not without their challenges. 1. Mode collapse. Sometimes the generator gets stuck producing only a very limited variety of outputs. Even though the real data has much more diversity, it finds one thing that fools the discriminator and sticks to it. 2. Training instability. GANs can be notoriously difficult to train. Balancing the two networks, ensuring they improve together without one overpowering the other, requires careful tuning. And often leads to oscillations or failures. 3. Evaluation difficulty. It is hard to quantitatively measure the quality and diversity of GAN-generated outputs, as traditional metrics often fall short. 4. Computational cost. Training high-quality GANs often requires significant computational resources and time. Generative adversarial networks represent a monumental leap in AI's ability to create. By pitting two networks against each other, GANs unleash a powerful learning dynamic that has pushed the boundaries of synthetic data generation. While challenges remain, research continues to refine their stability and expand their capabilities. From crafting hyper-realistic faces to aiding scientific discovery, GANs are not just fascinating theoretical constructs. They are practical tools shaping the future of digital content creation, data analysis, and beyond. If you found this explanation insightful, hit that like button. Subscribe to BlackBoard AI for more deep dives into the world of artificial intelligence. And let us know in the comments, what is the most impressive GAN application you have seen?